So what are the characteristic harmonics or the common typical harmonics for various different loads in a power system? That's a common question that we get a lot. So if I have a variable frequency drive or if I have a computer power supply, which harmonics am I going to see? Let's take a look at this table, and it pretty much defines some of the more common harmonics that you'll see on power systems based on the loads. So as I look at drives, whether it's a 6 pulse, 12 pulse, 18 or 24 pulse, they all follow the H equals NP plus or minus 1, meaning the harmonics that you see are N, which is an integer, times P pulse plus or minus 1. So if I have a 6 pulse drive, I'm going to have 6 plus or minus 1, 5th and 7th, 2 times 6 plus or minus 1, 11th and 13th, and so on. If I have a 24 pulse drive, I'm going to have 24 plus or minus 1 and 48 plus or minus 1 and so forth. EC motors look a lot like 6 pulse drives, so we're going to have a lot of the 5th, 7th. In fact, those harmonics are even more substantial in terms of the magnitude of the harmonics, usually based on the fact that they don't have line reactors or DC chokes inside the EC motors. But the characteristic harmonics are the same. Computer power supplies have all the odd harmonics. Fluorescent lights, again, all the odd harmonics. LED lights, very similar. Interestingly enough, I didn't have it on here, but a single-phase drive or a single-phase input on a 3-phase drive would give you the same characteristic harmonics for switch mode power supply or the LED lights. And then things like arcing devices, which would be like an arc furnace, or perhaps even we used to consider fluorescent lights to be arcing devices. Transformer energization, some of those things like that are short-term harmonic spectrums, which is going to be like in the transformer example, 2nd, 3rd, 4th. So again, when you turn on a transformer and you get that hum, you can see, like a zoom, and that hum has 2nd, 3rd, 4th order harmonics. So one of the important things, though, to recognize is that the magnitude of the harmonics decrease typically as you go up in frequency. So if I have a 6 pulse drive, my 5th harmonic is the most predominant, and then it decreases as I go up in frequency. Now, let's take a look at some example waveforms for some example typical characteristic type loads. So we'll look at 6 pulse, 18 pulse, computer power supply, and transformer energization. Here's an example of a 6 pulse drive, and so again you can see the typical, again, current harmonics that we see from there, and you have the fundamental or the 1st harmonic, and then you have the 5th harmonic and 7th harmonic, and then you have 2 times 6 for a 6 pulse drive, or the 11th and 13th, and 3 times 6, and so forth. And you can see that the characteristic waveform is that characteristic double hump current waveform. Now if we take an 18 pulse drive, which harmonics are we predominantly going to see? We're typically going to see the 17th and 19th, and then the 35th and 37th. If I take a look at a computer power supply, which harmonics am I going to see? I'm going to see all the odds. And in fact, like I mentioned earlier, the harmonics decrease as you go up in frequency. So which one's the most predominant here? It's the 3rd harmonic, followed by the 5th and the 7th and so forth. So the interesting thing on this graphic is that the neutral current, even though we have balanced phase currents, so 85 and 86 amps on the phases, I have a neutral current of almost double that, 145 amps. And that is predominantly the 3rd harmonic current. So as we look at currents in the phases and the neutral conductors, we have to understand which harmonics, which frequencies we're seeing on those conductors. Now here's transformer energization, and the waveform looks a little different than what we're used to. The one thing to notice about this waveform is that the top half of the waveform and the bottom half of the waveform are not the same. So when we have asymmetrical waveforms, meaning, again, even with the double hump 6 pulse current that we saw before, the top and the bottom, in other words, the positive and negative half cycles were the same. In this case, they're not. So which harmonics come out when they're asymmetrical like this? It's the even harmonics. So we have 2nd harmonic and 4th harmonic and 6th harmonic. So it's interesting, but when we look at characteristic waveforms for loads like this that produce second, third, fourth, fifth, those even harmonics, a lot of times we're going to end up seeing something that looks a little different in terms of waveform. But again, this is a short-term waveform that we see with transformer inrush. So when we talk about basically transformers, we talk about variable frequency drives, we talk about computer power supplies. Every one of those things that converts from AC to DC in terms of the rectifiers and things that we see in our power system, anything that's nonlinear load like that, they're going to produce characteristic or typical harmonics. And those waveforms are pretty similar across the board. The magnitude of the harmonic depends on the quality of the rectifier or the system that's built in terms of the current. But again, we can identify those things very characteristic, very similar across the board.